In this chapter, we'll do an introduction to gears. Okay, so we have gears are used in several applications. They are mainly used, for example, to transmit, if you want, torques, but with different angular velocities. So you can try to reduce the angular velocity sometimes, or you want to increase it. So it depends on your application. For example, your car transmission system is full of gears. Now we have several types of gears, and each one is used for certain application. So it depends what is the final output you need to have. This will allow you to select a set of gears that is convenient for your application. So we will divide the gears into several parts, and we'll be able at the end for a certain application to select the corresponding set of gears that will allow us to do the job required. Okay. Now in this part, which is gears introduction, we'll just introduce what are the types of gears, what are the main, if you want, driving relations that can be used to relate angular velocity of gears, etc. Okay. So Yella, 1 second, it's opening. Do you see the screen now with the PowerPoint? Do you see the PowerPoint?
Yes, doctor.
Okay, so as you can see here, we have several applications using gears. So here, for example, you can use this to create different speed ratios. You have in this mechanism, gears will allow you to achieve the appropriate objective, let's say, which is to cut some tools, etc. Now we have several configurations of gears. So we can have, the easiest configuration is friction wheels. So you know that to transmit action between two wheels, you need a tangential force. So if you only have at contact between wheels a normal interaction, this will not allow you to have rotation. So you need to create a tangential force transmitted between your parts. So to do this, you have several options. The first one is to have rolling cylinders, but with sufficient friction at the interface, because the friction at the interface will create this tangential force, which will lead to a rotation of your parts. So if you have if you have cylinders without friction between them, then they cannot transmit any tangential force from one to the other, and then you cannot consider that your system will work as you like. Okay, so one of possible transfer of rotary motion will be to use rolling cylinders, but the condition is to have enough friction at the interface between these cylinders. And you have several configuration. You can have here, as you can see, you can have internal contact or external contact. So in case of internal contact here, both cylinders will rotate in same angular velocity direction. However, here you will have opposite angular velocities, because what will be common is the force transmitted. And this force here will produce about this point a couple in the counterclockwise direction. However, it will produce about this point a clockwise couple. Okay. Now, if you consider here, for both, the force will produce, if you have a transmitted force like this, for both, it will produce a rotation into the counterclockwise direction. Okay. So we say that we have internal and external configurations. Now, you have for belts, you can use belts also to transfer rotary motion between parts. Okay, and you have several configurations of belts. They can be flat. So when we talk about flat or V belts specs, this means when we talk about flat or V, this means what is the shape of the cross section of the belt. So if you do a cross section for a flat belt, you will just see a rectangular cross section. However, for a V belt, you will, when you do a cross section, you can see this. Okay, and we'll see the application of each one. Okay, so in general, both can be used to transfer power through friction. So the friction between the belt's surface in contact with the rotating device here will allow to transfer a force, and this force will be transferred through this linear belt. Okay, and then it will be able to create rotation of the other part. Now, these types, flat and V belts, will be used for moderate power applications. So they cannot transfer very large powers. So they are just used for moderate power applications. And the condition is that you have enough belt cross section needed. So you should study what is the thickness of the cross section required to transfer such power. So larger the power to be transferred, larger should be the cross section of your belt. Now, the disadvantage of V belts and flat belts is that you have possibility of slip. So you can have slipping between the rotating parts and the belt. So this is why you cannot allow absolute phasing. What we mean by absolute phasing, so you can control perfectly with a certain instantaneously the rotation of the two parts. This is not possible with such system. Now, the advantage is that flat and V belts are quiet. They don't produce a lot of noise, and they are inexpensive solutions. And they are used a lot in sewing machines and in car alternatives. Now, you have, as we have talked, we have to distinguish flat and V belts. Okay, we look at the cross section. So as I told you, for flat belts, you just have a cross section that is rectangular. However, for V belts, you have several possible configurations. And of course, for example, the simplest one is the standard V. You just have a V cross section. And then, of course, the part that is rotating should be machined in a way to have this belt so that the belt can sit on it. Okay. Now, to transfer larger powers, you can play a lot with the configuration. You can create a double V configuration. You can create multiple V. So this will allow you to transfer larger powers. And sometimes even you use a cocked V configuration. So here, instead of having it just in this shape, you can create a cocked configuration like this. So also this will allow, if you want, the relation with the other part will be stronger. Now, another type of belt that is used a lot in case if you want synchronization is very important. So you need to have, you don't want to allow slip, you want to have absolute phasing between your parts. You can use what we call timing belts. Timing belts are used for synchronization purposes. So because they are characterized by within the belt you have teeth. Okay, so you can transfer power through teeth machined within your belt, and of course then your systems, your rotary parts will have gears also where the belt can set. And the advantage is that you can have perfect synchronization. You will not have slip between the parts. You have absolute phasing, so between rotation of different parts. But on the other hand, the disadvantage is that it's only applicable for lower power applications. And sometimes also one good thing is that you have this configuration available as double-sided time belts. So you can have teeth from both sides. Okay, and this will allow you to create serpentine applications where your belt is double-sided and can be used from both sides. Now, in gear systems, we have always teeth. Okay, so and as we said, teeth will allow a very good synchronization. You don't have slipping, so this is why gears are used a lot. Now, you can have in general you have input and an output, and we use such gears when the phasing of input and output is required for timing purposes. For the name of gears, we consider, and we just say gear. When we say gear and pinion, gear represents the larger of the two meshing gears, while pinion will be the smaller one in the set. Okay, so whatever you can just compare dimensions to detect what is your pinion, what is your gear. Now, we have several types of gears. We have spur gears that are very common, in which case you have that the teeth are parallel. So as you can see, the teeth are parallel to the axis of your gears, and they represent the advantage that they don't produce, they are simple. They are simple in configuration, but the disadvantage is that their operation will have a certain noise, will produce certain noise. Now, another type is helical gears. In helical gears, we have the teeth will have a certain helix angle. They will not be the axis of these teeth will not be parallel to the axis of the gear. This will allow a smoother and quieter operation, but of course they are more expensive. And we have several types of helical gears. They can be parallel or crossed. So when we talk about this, this means that the section of your gears is in one plane or not. So as you can see here in parallel configuration, the section of your gears is in one plane. However, here sections are in perpendicular planes. So this is a crossed configuration.
هاي دكتور كيفك؟ بس في نطلب طلب كبير. السلايد نمبر 5 يرجع نعيده من المعروف لانه الانترنت بالجامعه كان عم يعلق. ميرسي.
Okay. Look, in this slide we are just representing several configurations of V belts. Okay, for flat belts you just have a rectangular cross section. Okay, while for V belts you have different configurations, and the more complex the configuration is, this will allow you to transmit larger power or to have a safer interaction between the parts. Okay, so here for example for standard V you just have a V-shaped cross section, and of course the rotating part should have grooves within it so that the belt can be put in place. Now, more complex configuration include double V and multiple V, so this will help you into transmitting larger powers. And also you have a configuration which will make stronger if you want combination between the rotating part and the belt, which is the one with cocked configuration. So you can see here's a profile. This is a cocked configuration allowing a stronger interaction between if you want your belt and the rotating part in comparison with this one. Okay. So this is for the different configurations of V belts. Now we'll continue with the type of gears. So other types are worm gears. And in these gears, we have, we'll talk about after about what is an involute. So here, what will happen is that you have your worm gear is actually a strad, not an involute, and this is used to, if you want, for safety purposes, in order to prevent backdrive. Bevel gears are of the following. So this configuration represents bevel gears. Okay, so they are you have different configurations. They can be straight and they can be spiral. Then you will have, in case of straight, you have spur gears at a certain angle. So you have a certain angle between the gears. And for the spiral configuration, you have helical gears doing a certain angle between each other. So we encounter, depending on the application, we can encounter several types of gears. And one of also the used types is this one, consisting of a rack and a pinion. In this case, you will convert the rotational motion into a linear one. But in this system, the difference between this system and the worm gear configuration is that you can back drive here. So rotation is allowed in both directions. And this is called the rack. The rack will undergo translation while the pinion will do rotation. So in this case, you can convert rotational motion into linear motion. Now we'll start to talk about physics.
بس سؤال،
Yes.
الورم جير وين بيستعمل عادة يعني؟
الورم جير يستعمل بابليكيشن وقت ما بدك ممنوع ترجع لورا. اوكي يعني you can just allow motion in one direction. فبحيلا application you can only have forward motion not backward one فيك تستعمله. Okay.
Okay, thank you, doctor.
Welcome. So now you are already familiar with the fundamentals law of gearing. We'll do a small recapitulation of the laws. So the idea is whenever you use two gears in contact, you don't have slipping between them. The non-slipping condition will impose equal velocity at the contact point. Okay, so we can say velocity of A as a part of the pinion is equal to the velocity of A as a part of the gear. Okay, and now we know that linear velocity of a point can be related to the angular velocity of the gear. So we can say that this velocity as a part of the pinion, the velocity is r pinion times angular velocity of pinion. Okay, while I'm talking about, of course, the magnitude omega. Now, if you want to talk about algebraic values, okay, you should take a positive sense. So, for example, let us say we consider the positive direction counterclockwise. So the pinion here will rotate into the counterclockwise direction, and omega p will be positive. Okay, while for your gear here, according to the right-hand rule, will rotate into the clockwise direction. So omega gear will be negative as algebraic value. This is why we say that we can write that velocity at point A is equal to here plus r pinion times omega pinion equals to minus r gear times omega gear. Okay, and we can also use symbols of input and outputs. So here, if your pinion is the input and the gear is the output, then you can use the following names: Vn and Rn omega n, and V out R out omega out. Okay, now as I told you, sometimes just you should pay attention if you are talking about algebraic value or magnitude. If you are just talking about the magnitude omega, you can put Rn omega n equal R out omega out. Or if you want to talk about algebraic values, like here, okay, so here, for example, we can define what we call the angular velocity ratio. The angular velocity ratio is equal to the angular velocity of your output over the angular velocity of your input. Here, we are expressing omegas as algebraic values. Okay, in order to, if you want, differentiate between the internal configuration and the external configuration. I already told you that if you have an internal configuration formed by just two gears, then both will have same angular velocity direction and sense. Okay, so this is why here we'll take a general case, we'll express omega as algebraic values. Okay, and we'll say that whenever we have an internal configuration, then omega out and omega in will have same sign, same algebraic sign. So this is why the ratio mv for internal cylinders will be positive. While if we talk about external cylinders, this ratio will be negative. Okay, and from the relation we developed that the velocity should be equal, then we can, if we rearrange terms, because we said that, for example, here v input equal to omega input times r input, and if I talk algebraically, it's minus omega output over r output. Okay, then I can deduce that for external cylinders case, okay, what will happen is that the ratio of omega out to omega in will be equal to minus Rn over R out. Okay, while if I take an internal cylinder configuration, the only difference will be instead of minus, it's plus. Okay, and you know that the radius and diameter are proportional, so also it is equal to the ratio of diameters. So here you have the plus for internal configuration and the minus for external one. So to distinguish between these two, we take mv as the ratio of the algebraic values of angular velocity. Now, we have different configurations of gears, okay? So this depends on the profile of your teeth if you want. You can have, and of course, mating gears, teeth contours should be conjugates. So whenever you have two gears in contact, they should or both have involute configuration, or both should have cycloid configuration. So the cycloid configuration is represented here. So as you can see, you have a certain, the following profile, okay? While for involute, you have a certain characteristic shape of the teeth, and we'll go into detail about how the involute shape is designed. Okay, so it depends on the application. In general, cycloid tooths are found in watches and clocks, while involute curves are present in most of other gears application. In this course, we'll concentrate on involute configuration and we'll study how forces are transmitted through this configuration. So here, for example, we illustrate in the following diagram. Sorry. Okay. In the following diagram, we are illustrating, let me zoom it a little bit, the shape of an involute curve. Okay. And it's designed in a way, as we'll see together, that the force will be transmitted in a direction that is normal to contact between two teeth that are in contact with each other. And we'll see that if I take the base circle, so this is the base circle of my gear, okay, and I draw tangent lines from the base circle, then the involute curve will lie on different points of on these tangents. Okay, so I can define a certain shape for the involute. We'll talk about this into details when we see the transmission of forces in case of involute teeth. Now, to start with, let us start with some terminology related to gears. Okay, so first, the first concept to know is what is a pitch circle. So whenever here, for example, you have two gears in contact, okay, you can then define several parameters. The first one is the pitch diameter, which is related to the diameter of the pitch circle. What is a pitch circle? Whenever you have gears in contact, you will have certain contact point between the teeth. And these contact points will define a certain distance between the contact point and the center. So whenever you have gears in contact, you can define what is called the line centers. The line centers is joining your centers. And you can see that contact, you will have at least a contact point. So we'll see that in contact, not only you have one contact point, you have several contact points between T's. So, and at least one of contact points will be along the line of centers. And this contact point, which lies on line of centers, will always be at the same equal distance from the centers. Yani, if you measure at any contact point, the distance between this contact point and the first center D1, and the distance between the contact point and the other center, these distances will not change with time. So you know that when your gears will rotate, you will have new contact points, but you have one of these contact points lying on the line of centers, and the location of this point is fixed. Okay, so this is why we can define from here what we call a pitch circle. The pitch circle will be characterized by a diameter equal to for the big, so if this is gear 1, this is gear 2. Okay, let us call this R, so because it's a radius, and this is R1, R2. So the pitch diameter for gear 1 is 2 times R1 equal to D1. And for gear 2, it's 2R2 equals to D2. And as I mentioned, this is a constant, so this will not change. So whenever you have rotation, the contact point lying on the line of centers will always be at same distance from center 1 and same other distance from center 2. So we say that the pitch circle is an imaginary circle that rolls without slipping. So we have rolling without slipping at the level of contact at pitch circles. So it's rolling without slipping with a pitch circle of the mating gear, and it's the equivalent circle of friction rollers. So we have seen that the basic type to produce transfer of rotation is friction rollers. Okay, and then here the difference is that when you put teeth, you can ensure always a transfer of forces. However, for rollers, you should always check for that you have enough friction that will allow the transmission of rotation. While in the gear configuration, you can always, you can say that I can ensure that force will be transmitted between my 2 ports. So this is for the pitch circle and pitch diameter. Now, another important concept is what we call center distance. Okay, so the center distance is defined as the shortest distance between non-intersecting axes. So you have already gears. Each gear is characterized by an axis. Okay, and then we can define the perpendicular distance between the two, which is the minimum distance between these axes, and then it will be measured along mutual perpendicular to the axis, which is called the line of centers. Okay, so when you join centers of your axis, you can measure then the distance, the shortest distance between your non-intersecting axis. So this line is called line of centers, and then this distance or line of centers can be measured in spur gears, parallel axis, or crossed axis helical gears, and also in worm gears. And of course, if you have external gears, so it will be equal to, so here to the summation, if you want, of these two distances, while in internal gears, it will be equal to the difference between this distance and this one. Okay, so we can see here, we'll see after all formulas that will be used. So they are simple formulas. Now, Another important parameter to define is the tooth height. And the tooth height will be divided into two parts, addendum and dedendum heights. The addendum height is defined as the height that project beyond the pitch circle, while the dedendum height is the height from bottom of tooth to the pitch circle. So if we go back to our figure, we said that we can define the pitch circle. So once you determine the level of your pitch circle, which consists on, as we said, it's determined by the contact point between the involutes lying on the line of centers. This will allow us to determine the pitch circle diameter, and then we can draw it. You will see that your pitch circle will lie between the top and bottom of your involute or teeth or tooth. And then here you can define two distances. The distance between the top, if you want, circle and the pit and the circular and the pitch circle. This distance is called addendum. And the distance between the pitch circle and the bottom of your tooth is called dedendum. Okay, and we'll see together that we have relations between these and the pitch diameter. Now you can define also what we call, we'll see in other slides, what is clearance, what is circular pitch, and what is face width. So we'll detail these terminologies in next slides. So the other concept that is important is clearance. What do we mean by clearance? We have the clearance circle is the largest circle that is not penetrating mating teeth. What do we mean by this? So whenever you have contact, you will have, if you want, the tooth of the other, the teeth of the other gear will penetrate here, this gap. Okay, but for example, if you observe the maximum distance of penetration, you will see that you still have a certain gap here. So in general, you can have some, if you want, if some specific cases where you can reach the bottom, but it's not advised to have this. Okay, so we say that for a certain configuration, we define the clearance circle, okay, as the largest circle that is not penetrating the mating teeth. So if I consider the following case, okay, I can draw a certain circle that will not penetrate the mating teeth, so like this. And then I will define a certain distance between what we call the clearance circle and the bottom circle or the base circle. Okay, this distance here between the two is called clearance. Okay, so clearance can be defined as the radial distance from the clearance circle to the root or base circle. Now, other terminologies, we have the face width. What do we mean by the face width? The face width of the gear is the length of teeth in an axial plane. And for double helical, it does not include the gap. What we mean by this, so here you have the following case. Okay, so if you take if you want an axial plane, the axial plane will give you this cross section. You can determine from here what is the width of the face of your tooth. Okay, and you have sometimes what we call double helical configuration, where you will have, if you look at the profile here, you will have two parts that are very close to each other within a gap in between. In this case, you don't, when you want to calculate the face width, you should not consider the gap in between, so you should subtract it. Okay, so the total face width will not include the gap between if you have a double helical configuration. Now, other terminologies used, we talk about the whole depth of a tooth, okay? The whole depth is the summation of the addendum and addendum circles radiuses. And you have that the working depth, on the other hand, will subtract the clearance. We consider that the working depth is the whole depth minus the clearance. So this will be the working depth where you have penetration between the two gears in contact. Now, we'll start to define some important features that you will use to characterize gears. The first number we'll go over is the circular pitch. Okay, the circular pitch will represent the sum of the tooth width and the tooth space. What do we mean by this? So if you move on the pitch circle, okay, you have like a repetitive pattern. You have a tooth, then a space. Okay, so we say that the circular pitch, which is moving over the pitch circle, is the summation of the tooth thickness on the pitch circle plus the width of space between two teeth on the circle. Okay, and this number is important, and it can be related to the circumference of the pitch circle and the number of teeth. So we can say that the circular pitch can be calculated because it's a repetitive pattern, yani, where you have a repetitive pattern of tooth thickness and width between teeth of your gear. Then you can say, if I compute the total circumference of the pitch circle and I divide it by the number of teeth I have, I will get the repetitive pattern length, which is the circular pitch. So to calculate your circular pitch, you just have to divide the circumference of the pitch circle, which is pi times d, over the number of teeth of your gear. Another parameter that we also use in gear terminology is the diametral pitch. Okay, when we talk about the diametral pitch, it is the number of teeth of a gear divided by the diameter of the pitch circle in inches. So please pay attention for units. Okay, so in general, okay, we use d in inch. In case you use it in millimeter, it's not a problem, but you should specify. And in tables in general, they will give you that it's given in inch -1, or in if you want to use SI units, they can provide it for you in millimeter -1. So in the table, it should be clear which units is used. Now, we already defined the circular pitch in the previous slide. We said that it's equal to pi d over n. So we can find a relation between the circular pitch and the diametral pitch. We can just say from the following definition here, okay, that d can be replaced. So the pitch diameter, if you want, can be replaced by n times p over pi. Okay,